Hey everyone! Today we are going to solve rational inequalities. Let's acquaint ourselves with the step-by-step guideline. The first step for solving a rational inequality is to state the excluded values. The excluded values are the values that make a denominator equal to 0. So in this first example, we have a rational inequality such that the denominator is equal to a plus 1. So what we do in order to determine what would make that denominator equal to 0 is we set up a little miniature equation. We say a plus 1 is equal to 0. Solving for a, we'll subtract 1 from both sides, and we get that a is equal to negative 1. Some of us can tell that that would be the value of a that would make the denominator 0 at a glance. But just to be safe, for when our denominators can be more complex, we can set up a miniature equation. So we've now completed step 1. Step 2 states to solve the related equation, which is to replace the inequality symbol with an equal sign. So in step 2, I'm going to set up a new equation, which is called the related equation, simply by replacing this inequality symbol with an equal sign. Now let's solve the related equation. In this case, we have a rational expression set equal to an integer. What we could do here is set up a proportion. Let's write that as 3 over 1 and cross multiply. When cross multiplying, we multiply the denominator on one side to the numerator of the other side. So I'm going to multiply 3 through to the a plus 1. So let's wrap parentheses around that so that we don't forget to distribute. So I end up with a 3a plus 3 set equal to, let's cross multiply here, the 3 times the 1, which is 3. Now solving for a, I subtract 3 from both sides. 3a is equal to 0, therefore a is equal to 0 when we divide both sides by 3. So we've now completed step 2. Step 3 states to use the values determined in steps 1 and 2. Well, that would be a equals negative 1 and a equals 0. To divide a number line into regions. So step 3, I'm going to set up a number line. Into 3 regions. I have an a equals negative 1 and an a equals 0. So I now have my number line set up into 3 different regions. The other thing we want to consider is whether or not negative 1 is a solution to our inequality or 0 is a solution to our inequality. 0 makes this a true statement. So I'm going to make a solid dot on 0, and negative 1 makes our denominator equal to 0. So this is not going to be included in our solution set. So I'm going to put an open circle on the negative 1. Next, what I want to do is test each region as it states in step 4. So I'm going to test negative 2, which lies to the left of negative 1 on my number line. So this is what I'm testing right here. Negative 2 gets me a value of 3 over negative 2 plus 1 on the left side is it true that this is larger than 3? When plugging this in, we end up with 3 over negative 1, which would be negative 3. And this is certainly not equal to or greater than 3. So the values that lie to the left of negative 1 will not satisfy our original inequality. Now let's test a value between negative 1 and 0. Let's test negative 0.5. When I plug negative 1/2 in for a, I end up with a positive 1/2 in the denominator. 3 divided by negative 1/2 we're trying to find out if that is greater than or equal to 3. Sorry, did I say negative 1/2? You knew I meant positive 1/2 in the denominator. Remember, this is a result of plugging negative 1/2 in for a. Therefore, the denominator is equal to positive 1/2. So my resulting inequality as a result of plugging negative 1/2 in is 3 divided by 1/2. 3 divided by 1/2 is the same thing as 3 times 2, which is 6. And 6 is greater than or equal to 3. Therefore, since negative 1/2 worked, all of the small values in between negative 1 and 0 will work. And last but not least, let's test to make sure that this last region works, or if it doesn't work. So let's test, say, positive 1, or I'm going to actually test positive 2. So when I plug positive 2 into my inequality, I end up with 3 divided by 2 plus 1. And is it true that this is greater than or equal to 3? Well, since the left side simplifies to 3 divided by 3, which is just 1, I can conclude that this is certainly not true. 1 is not greater than or equal to 3. So the values to the right of 0 on the number line do not satisfy my original inequality. So now we've satisfied step 4, again, which was to test a value in each region to determine which regions satisfy the original inequality. Step 5, we want to state the solution as a concise algebraic inequality. So, looking at my number line, I can write this as an algebraic compound inequality such that negative 1 is less than a, which is less than or equal to 0. This is my solution set that will satisfy my original inequality. Let's try that again in this example. We have the inequality such that 1 over 4a plus 5 over 8a is strictly less than 1/2. So remember, our first step is to state the values that would make our denominator equal to 0. So I have a 4a. If that were equal to 0, then a would be 0. If 8a were equal to 0, that just means that a would be 0. And this third denominator is just a numerical value, so we can ignore that for finding our excluded values. Therefore, a can be equal to 0 is our excluded value on the number line. So now we've done step 1. Remember, step 2 is to solve the related equation by replacing my inequality symbol with an equal sign. So I end up with 1 over 4a plus 5 over 8a is equal to 1/2. Now, we have a rational equation similar to ones that we've been doing recently. So what we need to do is identify our LCD, which is an 8a, and we'll obtain that by multiplying the top and the bottom of the first fraction by 2. The top and the bottom of the second fraction can remain as is, since it already has my LCD, and then multiply the top and the bottom of the last fraction by a 4a. Now that we have fractions with like denominators, we can now cancel those denominators. And in the next step, our equation is 2 plus 5 equals 4a. Now let's finish this off. I have a 7 equals 4a. Therefore, dividing both sides by 4, we end up with a is equal to 7/4. We have now completed step 2. Step 3 is to make sure that we plug these two values from step 1 and 2 onto our number line. So step 3 was to make sure that we put our excluded values and any values we found in step 2. So now I have a value of 0 on my number line, and I will put an open circle on this value, since we do not want to include that in our solution set, since it is an excluded value. And the boundary point of a 7/4 that we found is also going to be an open circle, because our inequality is a strict inequality, meaning let's not count that boundary point either. Now that we've broken our number line up into 3 different regions, let's test each region. Step 4 is to do so. So I'm going to test -1 first. So when I plug -1 into my inequality, I end up with this statement. We want to verify if this is true. The first fraction, we've got -1/4. To combine that with the 5/8, let's multiply the top and the bottom by 2. Well, the next step, I would end up with a -2/8 plus -5/8 for a grand total of -7/8. That is certainly less than 1/2. So all of the values that lie to the left of 0 will make this a true statement. Now let's test a value between 0 and 7/4. I'm going to say 1. Let's test 1. Let's notice that when I plug 1 into my original inequality, I end up with 1/4 plus 5/8. And we're trying to find out if it's true that it's less than 1/2. So let's put a question mark here. So again, let's convert this first fraction such that it has a denominator of an 8. And then we have 2/8 plus 5/8. Is it true that 7/8 is less than 1/2? Certainly not. Since this is not true, the values that lie between 0 and 7/4 will not satisfy my original inequality. Now we've got one more region to test. Let's test something greater than 7/4. Say 2. So when we plug in a 2, we end up with 7/16 on the left side of our inequality, which is less than 1/2. Therefore, all of the values to the right of 7/4 will satisfy my inequality. Therefore, the values to the left of 0 and the values to the right of 7/4 will satisfy our inequality. Therefore, this is our solution set. This now concludes our introduction to solving rational inequalities.
Made with Doodlecast Pro.